everybody, welcome to another video. Hope you're ready to flex those brain muscles. So if you missed my last video, you can click right up here. It was an introduction to limits. I introduced the basic idea. We sort of built a foundation to continue moving forward talking about limits. So in this video, I thought it would be a really good idea to just do a bunch of examples and find a bunch of different limits and give you all the opportunity to practice. So that's exactly what we're gonna do. I went ahead and made a worksheet of a bunch of examples of finding different limits, and I'm gonna put that in the description below. So I strongly suggest, again, because this is your opportunity to practice, I strongly suggest before you move forward with this video that you either print or download that file, that PDF, and try these on your own, all right? Try to find these limits on your own and then watch my video. And the reason I say that is because math is not a spectator sport. It's really hard, at least in my experience, it's hard to learn math just by watching someone else do math. You have to really try it on your own. So that's why I suggest that. Try this on your own and then use my video to check your answer or to sort of, fill in the gaps of where you're lacking in understanding, all right? So moving forward, let's go ahead and start finding some limits. I do have a chalkboard today. This is all I have access to. So if the chalk is okay, then let me know. I'm not sure how I feel about it yet, but yeah. If it sucks, then let me know in the comments and I'll go back to my whiteboard, that's fine. But we're gonna find some limits. So number one, here's our first example. What's the first thing we always do when we're finding a limit? We just plug the number into the function and see what happens, right? Because if we plug the number in and we get a real number as an output, then that's our limit. So let's see if that happens here. So I plug in 3 to this function, and I usually do this off to the side, all right? So 3 squared, that gives me 9 minus 13. So this is gonna be a real number, all right? 9 minus 13 equals -4. So again, we plugged our number into our function, we got out a real number, so this real number is our limit. All right, here's our second example. So same thing every time, plug our number into our limit, see what happens. So I'm gonna plug 4 into this limit, and I get the square root of 4 squared, that's 16, minus 10. And this equals the square root of what? 16 minus 10, that's 6. Okay, so I plugged in my number 4, right? When x is approaching, I'll plug that in. I got out square root of 6, which is a real number, okay? We don't care that it's an irrational number, it's a real number. So that is our limit, square root of 6. All right, so now that we got the easy ones out of the way, let's go ahead and look at example number 3, the limit of this rational function as x approaches 5. So we start out the same way, plug 5 into our function and see what happens. So when we do that, we get 5 minus 5 over 5 squared, that's 25, minus 4 times 5, that's 20, minus 5, and this equals 0 over 0, which is undefined, right? So we didn't get a real number, so now what do? Well, this 0 over 0, and I just want to clear something up real quick because in my last video, in the introduction to limits, I said 0 over 0 means that we have a whole. Well, that's not always the case. That's the case about 98% of the examples we'll see. 0 over 0, we can say we have a whole, but it's not always the case because consider this, and this is the only time I'll talk about this, but I do want to just make note of this. Consider the limit as x approaches 0 of x over x squared, all right? Look what happens when I plug in 0. I get 0 over 0. But what happens when I reduce this function to 1 over x? Now when I plug in 0, I get 1 over 0, all right? So this limit actually does not exist. So be careful, you don't always have a whole, usually you do. So here's how you tell, all right? When I reduce this rational function to its lowest terms, which is what I did from this step to this step, I reduced because I canceled an x with an x, right? I reduced to its lowest terms. If I can plug this number, x is approaching in, and get a real number, then it turns out it was a whole, right? And that real number I got out is my limit. If I plug it in and I still get something that's undefined, like in this case, I plug in 0, I get 1 over 0, it's still undefined, then it is an asymptote, all right? So just be careful of that, make note of that. I apologize, I didn't make that clear enough in my last video. So 0 over 0 means most likely a whole. That's the phrase I'm gonna use moving forward. 0 over 0, so we probably have a whole, but we have to double check. And we will find out just once we start reducing this to lowest terms, we're gonna find out. So, okay, let's move forward with this example now. So 0 over 0 means we most likely have a whole. So how do we find out for sure we reduce this function to its lower terms, right? So since we got 0 over, all right, so we plugged in the number x is approaching, we got 0 over 0, which means we most likely have a whole, all right? So how do we find out for sure? Well, we're gonna reduce this to its lowest terms, and since we do have a polynomial over a polynomial, the first thing I'm gonna try to do is factor, because when you have a polynomial over a polynomial, right, a rational function that looks like this, factoring is usually going to work. So let's see if I can factor the bottom and somehow cancel maybe an x minus 5. All right, let's try this. So if I factor the bottom, I have x minus 5 up top. I'm looking for basically two numbers that multiply to be negative 5 and add to be negative 4. So let's see. I think minus 5 and plus 1 will work. And that is going to cancel my x minus 5. So x minus 5, x plus 1. And I can FOIL this out and see if I get back to here, which I do, if I want to double check my factoring here. So x minus 5 can cancel with the x minus 5. So what's the only difference between these two functions now? So the only difference between these two functions is that the graph of this function as a whole, where x equals 5, and the graph of this function doesn't, all right? So the whole is basically filled in with the graph of this function, which is why it works when we plug 5 in. We do get a real number. We get 1 over 6, which is our limit because that's the y value for our whole, right? Think about what a whole looks like, something like this. So if we're approaching, right, if this is our x value we're approaching for both sides, then our limit is going to be the y value for that whole, which is what happens when we plug 5 into this function. So that's why this works out, but hopefully that makes sense. So let's go and move forward. All right, example number 4. First thing we're going to do, plug 0 into our function. We get 5 times 0, that is 0, plus 4. So that's 0 plus 4 all under this square root, minus 2, over 0, all right? So what is this top simplified to? Let's see, 0 plus 4, that's just 4. Square root of 4, that's 2. 2 minus 2, that's 0. So this is 0 over 0, so we most likely have a whole, but we can find out for sure by reducing this function to its lowest terms, all right? And we don't have a polynomial over a polynomial. I'm not gonna be able to factor this, but what should jump out to you is this square root and the way this is sort of set up, this numerator, right? And it should jump out at you to use the conjugate. And if it doesn't jump out at you yet, then just keep doing examples. Eventually, it will be obvious that, oh, for this kind of example, I'm gonna use the conjugate, right? So that's what I'm gonna do, is I'm gonna multiply the top and bottom by the conjugate, which is just keeping basically everything the same. All I'm doing is I'm changing this minus to a plus, all right? And we're gonna see why this works out so well. So 5x plus 4 plus 2, and I gotta multiply the top and bottom like this because I don't wanna actually change our function, right? This is a form of 1. 5x plus 4 plus 2. So look what happens when I multiply this numerator by this conjugate. So the square root of 5x plus 4 times the square root of 5x plus 4, that just becomes 5x plus 4, all right? So that's what I have in the numerator, 5x plus 4. And then look what happens to these middle terms. Look what happens to the radical, all right? Square root of 5x plus 4 times 2, all right? So that it'll be plus 2 times this radical. And then I get minus 2 times this radical. Those middle terms cancel, and that's why this works so nicely. So all I'm left with is the first, right? First, the outer and inner cancel, and then the last is what I'm left with as well. So negative 2 times positive 2 is minus 4, which gives me just 5x. And in the bottom, I have x times this whole guy. So what I strongly recommend doing is don't actually distribute this x out, because look what we have in the numerator. We have a factor of x in the numerator, and we can kind of reach over and cancel, all right? So I would just rewrite the denominator as x times this conjugate term, all right? So square root of 5x plus 4, because look what happens. If you distribute it out, you're gonna end up factoring it out to cancel, which is kind of working a step backward and then a step forward. It's kind of, you know, so this is what I like to do. So I'm gonna cancel these x's. And now look what happens. I have 5 over square root of 5x plus 4 plus 2. And now look what happens when I plug 0 into my function. I get 5 in the numerator, I'll write it down here, equals 5 in the numerator. In the denominator, I get 0 plus 4, okay, all under the square root. So that's the square root of 4, that's 2. 2 plus 2, so that's 4. So my limit is 5 over 4 because I reduced this into its lowest terms, right? Because I canceled an x in the numerator and denominator. I reduced this, I was able to plug this number in and get a real number, therefore it turned out it was a whole. So now what? My limit is 5 over 4. So this limit equals, let's see, I'll just circle it down here, 5 over 4. All right, example number 5, we go ahead and plug 7 into our function and see what happens. We get 4 in the numerator. In the bottom, we get 7 minus 7, that's 0, and 0 squared is 0. So what does this mean? Well, this means that we have a vertical asymptote where x equals 7. That line x equals 7 is a vertical asymptote. So what happens when we approach an asymptote from both sides? Well, our limit doesn't exist, right? But we do have the possibility for what we call an infinite limit. So what that means is even though our real valued limit does not exist, sometimes we are expected to specify, is the function increasing without bound? Then we would put infinity. Or decreasing without bound, we would put negative infinity. So depending on your instructor and the way you're being taught, maybe you could just write DNE, but I'm gonna find out. I'm gonna see if this is increasing, decreasing, or if I can just flat out put does not exist. But again, the real value limit, the limit doesn't exist, okay? But we just specify. It is a little bit tricky. So how do we find out? Well, I'm gonna look at 7, since this is an asymptote, and I'm gonna find out what's happening around 7. So I kind of do need to plug in some numbers. So maybe I'll plug in over here, I'll plug in 6 and 6.5. And then maybe here I'll plug in 7.5 and 8. All right, and I'll sort of see what's happening. Is it increasing, decreasing? And then I'll come up with whether it's infinity, negative infinity, or just flat out does not exist. So there's 2 ways you can go about this. You can use your calculator and plug in numbers. And if you do that, you will see that as x approaches 7 from the left, my y values are getting bigger and bigger, and the same from the right. So we could write an infinite limit of infinity, which is true. But there's another thing you can notice. This denominator is a squared term. So maybe you could have been able to figure this out without having to plug in numbers and use a calculator. Since the denominator is squared, it's always positive, right? No matter what I plug in for x, that denominator is positive. So there's no way we can be negative. So we can't really approach negative infinity. And another way to think of it is that what happens as x gets closer and closer to 7, this whole denominator gets smaller and smaller, and as a denominator gets smaller, the value of the entire ratio gets bigger, all right? So a few different ways to think of it, but again, you always want to check and make sure because you could have an infinite limit, especially if your instructor wants you to specify whether it's increasing or decreasing without bound. So in this case, as x approaches 7 from either side, our y values are increasing without bound, so we say it as an infinite limit of infinity. All right, number 6, the limit as x approaches 0. So what do? We go ahead and plug in 0 to our function. So I get 0 cubed, that's just 0, minus 4 times 0, that's 0. Let's see, 0 squared is gonna be 0, so 2 times 0 is 0. Oh, this is gonna be 0 over 0, okay? So that means there's most likely a hole in the graph of this function, so our limit will most likely exist. But how do we find out for sure? Well, we need to reduce this function to its lowest terms and then plug in 0 and see if we get a real number. So how can I reduce this function to its lowest terms? Well, since it is a polynomial over a polynomial, I'm gonna look to factor. And what jumps out to me in this example is the fact that there's an x in common between everything. Everything shares an x. So I can factor out an x from the numerator and denominator and cancel those x's and see if I can then plug 0 in and have it work. And I think it will. So in this case, let's see what I can go ahead and do. Factor out an x from the numerator, I get x times x squared minus 4 over, factor out an x from the denominator, I get x times 2x plus 3. These x's I can go ahead and cancel. And now look what happens as I plug in 0. I get 0 squared minus 4, that's negative 4, over 2 times 0, that's 0, plus 3, that's 3. So since I was able to reduce this to its lowest terms, plug 0 in and get out a real number, that real number is my limit. So the limit of this rational function as x approaches 0 is negative 4 over 3. All right, number 7, the limit of this crazy looking function as x approaches 0. So let's plug 0 in and see what happens, all right? So I get 1 over 0 minus 1, that is negative 1, plus 1 over 0 plus 1, that is 1, which equals 0, that's in the numerator, and then I get 0 in the denominator as well. So there's most likely a hole. I'm gonna go ahead and look and see if I can reduce this to its lowest terms. Okay, so what jumps out at me about this example is the fact that I have these crazy fractions in the numerator. So what I'm going to try to do is find a common denominator, see if I can combine these fractions in the numerator, and see if I can then cancel this somehow and reduce it. So that should be the hint for this one. When you see stuff like this, find a common denominator, start combining stuff, whether it's in the numerator or denominator. Combine your fractions and see what happens. So I'm going to go ahead and do that in the numerator. And it looks like my common denominator is going to be x minus 1 times x plus 1. So basically I'm going to multiply this fraction by x plus 1 over x plus 1, and this one by x minus 1 over x minus 1, and then I'll be able to combine them. So let's go and do that and see what happens. If I multiply this by x plus 1 over x plus 1, I get x plus 1 over x minus 1 times x plus 1. And when I multiply this one by, let's see, x minus 1 over x minus 1, I get x minus 1 over x minus 1 times x plus 1. So now I have a common denominator. I can combine these into the same fraction, or the same denominator, all right? So this equals what? X plus x, that's 2x. 1 plus negative 1, that's 0. So I'm left with 2x in the numerator. And then the denominator, I have x minus 1 times x plus 1. But this is just the numerator, so this is still all over x, but I'm going to write that as x over 1. And the reason I do that is because most students, when they have a fraction over a fraction, they know to flip the bottom fraction, and multiply across. So I can actually go ahead and do that. 1 over x, right, because I'm dividing two fractions, I can take the reciprocal of the denominator, right, the bottom fraction, and multiply. And now look what happens. X cancels with x, all right? So since the x is canceled, that kind of becomes a 1. So I'm multiplying by 1. So I don't even have to worry about this piece anymore. So I have 2 over x minus 1 times x plus 1. So let's see what happens when I plug in 0 now. So let me go ahead and simplify this. 2 over x minus 1 times x plus 1. Let's see what happens when I plug in 0. I get negative 1 times positive 1, which is negative 1. So I get 2 over negative 1, which is just negative 2. So hopefully that makes sense. It should jump out at you when you have fractions that are separate in the numerator or denominator. Combine them, get a common denominator to combine them, and then see if you can reduce to its lowest terms by doing that, by sort of combining the fractions using a common denominator. So hopefully that makes sense. Our limit is negative 2. All right, example number 8, we have the limit of this function as x approaches 1. So what's the first thing we do? Plug 1 into the function and see what happens. So we get 1 minus 1, that's 0 in the numerator. Under this square root, we get 1 plus 3, that's the square root of 4, which is 2. Minus 2 is 0 in the denominator as well. So we most likely have a whole, and our limit most likely exists, but how do we find out for sure? We gotta reduce this to its lowest term. So how do we do that? We saw an example very similar to this earlier. So hopefully it jumps out at you. We'll say it on 3. 1, 2, 3, conjugate. That's right, conjugate. You already knew. You're probably already checking your answer by now anyway. You probably already have the answer. You're like, shut up and give me the answer already. So we're gonna use the conjugate. So I'm gonna multiply top and bottom by square root of x plus 3 plus 2. Top and bottom, square root of x plus 3 plus 2. All right, so what happens when I do this? So this time in the numerator, I'm gonna be left with something crazy, but I'm just gonna keep it like this. I'm not gonna FOIL anything out yet, because I have a feeling something will cancel without having to do that, but we'll see. I can always go back and do it at the end if I need to. So I'm gonna start with the denominator actually in this case. So square root of x plus 3 times the square root of x plus 3 is just x plus 3. So I have x plus 3 in the denominator. Remember, this is the denominator. Remember, my middle terms cancel. That's how the conjugate works. That's why we pick the conjugate, because it gets rid of all the radicals in whichever term has the radical, right? So we got rid of all the radicals in the denominator. So again, those middle terms cancel, so I get x plus 3 minus 4, all right? Because negative 2 times positive 2. This simplifies to what? X minus 1. And now we see why we didn't FOIL that numerator out. Because look, x minus 1 in the denominator, and x minus 1 in the numerator, all right? So I'm just gonna reach up here and cancel that. Hopefully y'all follow that. I simplified, or I FOILed out the denominator, and I got x minus 1, which cancels with a term in the numerator. So what am I left with? 1 in the denominator, and in the numerator, I'm just left with this conjugate term, square root of x plus 3 plus 2. So now what happens when I plug 1 into my function? I get 1 plus 3, that's the square root of 4, that's 2. Plus 2 is 4 over 1. So I actually get 4 as my limit. So the limit as x approaches 1 equals 4. All right, example number 9. The limit as x approaches 1, so I'm just going to go ahead and plug 1 into this function. I get 1 to the 4th power minus 1, that's 0, over 1 to the 3rd power minus 1, that's 0. So I most likely have a hole in the graph of this function, but I need to reduce it to its lowest terms to find out for sure. So how can I do that? Well, we do technically have a polynomial over a polynomial in this case. And there is actually a way that we can factor both of these, although it's a little bit tricky. Maybe you won't see it at first, but hopefully after I show it, you will recognize it for future examples if this does come up. So in the numerator, we have x to the 4th power minus 1. This is actually a difference of squares, all right? So x squared squared, that's x to the 4th. So we have something squared minus something squared. 1 squared is 1, all right? These two things are the same. So my a is x squared, my b is 1, and I can actually factor this x to the 4th minus 1, and it becomes x squared minus 1 times x squared plus 1, okay? So let me erase this sort of scratch work here. And now what can I further do? I can factor again. This is a difference of squares, okay? So I can factor this down again, and it becomes x minus 1 times x plus 1. And I got that from this x squared minus 1. My a is x and my b is 1 again, right? X minus 1, x plus 1, and I'm still left with this x squared plus 1. Okay? So that's all in the numerator. Now let's look at the denominator, because I don't see anything I can immediately cancel, so maybe I can factor the denominator somehow. Does it jump out at you yet? So this is actually a difference of cubes. My a is x, my b is 1. So we need to use the difference of cubes formula, which you've probably forgotten. So did I, it's okay. But I do remember the acronym SOAP, same, opposite, always positive. So I know that this factors to, let's see, it's gonna be same. So x minus 1. And then this is gonna be opposite. So x squared, opposite is going to be plus x, always positive. Same, opposite, always positive, plus 1. All right, I believe this is right. Let me just double check this. All right, I double checked and this is in fact correct. So now look what happens. X minus 1, x minus 1. Those are both gone. So now what happens when I plug in 1? Let's see if it works now. 1 plus 1, that's 2. Let me write this off to the side here. 2 times 1 squared, that's 1 plus 1, that's 2 times 2 in the numerator. In the denominator, I get, let's see, this is gone, so I get 1 squared plus 1 plus 1. That's 1 plus 1 plus 1. So I get 2 times 2, which is 4 over 3, and that's my limit, 4 over 3. So a little bit tricky just because you have to recognize that this is a difference of squares, and then once you factor that, there's another difference of squares, and you have to recognize that this is a difference of cubes. But I put this in here just in case this comes up. It's better to be confused now sitting at home watching a YouTube video than it is on a quiz or an exam. So that's why I put this example in, but let's go ahead and move on to the next example. All right, for example 10, I have a one-sided limit. I thought I'd throw one of these in just for everybody to get some practice. So we have the limit of 1 over x minus 3 as x approaches 3 from the left. So again, one-sided limit. So we can still plug 3 into our function and see what happens. It may help us. So when I plug 3 in, I get 1 over 3 minus 3. That's 1 over 0, all right? Which means we have a vertical asymptote. The graph of this function has a vertical asymptote at x equals 3. So I can think about it this way. I can write 3 here. I have a dotted line here. That's my vertical asymptote at x equals 3. So what's happening as x approaches 3 from the left? Well, there are really only two possibilities. Either x is increasing without bounds, so we're doing something like this, headed toward infinity, right? Or decreasing without bound. So these are my two possibilities. So the real value limit, again, does not exist, the real value limit, but we do have an infinite limit that we want to specify whether it's infinity or negative infinity. So how do I find out? Well, I can just plug in some numbers. I can plug in 0, 1, 2, and 2.5 or something like that and see what's happening to the y values as my x values get closer and closer to 3 from the left. So I'm going to go ahead and do that. Let's see. F of 0. So what happens when I plug 0 to this function? I get 1 over 0 minus 3. That's negative 1/3. F of 1. What happens when I plug 1 to this function? I get 1 over 1 minus 3. That's negative 1/2. All right, so what about f of 2? What happens when I plug 2 in? I get 1 over 2 minus 3, that's negative 1. And let's try 2.5. I think I can do this without a calculator. Last time I used a calculator, but I thought maybe if you're not allowed a calculator, I'll show you how you can do it without, okay? So when I plug 2.5 in, I get 1 over 2.5 minus 3, that's negative 0.5. So that's actually negative 2. So my values are getting, let's see, smaller and smaller, right? So we are headed toward negative infinity because my y values, as my x values get closer and closer to 3 from the left, my y values are getting smaller and smaller. We're decreasing without bound. So we do have an infinite limit, and we can specify that it is indeed negative infinity. So hopefully that makes sense. So these last 3 examples fall under the category of limits at infinity, which I haven't talked about yet, but will be making a video on pretty soon within the next couple of weeks. So for the purpose of this video, I will just quickly talk about these 3 examples and even show a little shortcut to help you find limits at infinity. But first, let's go ahead and talk about it. The limit of this rational function as x approaches infinity. So what does it mean for this to exist, right? If a limit at infinity exists, what does that mean? Well, that means as my x values get bigger and bigger and bigger, my y values are approaching some real number, all right? So what does that mean? Well, that means the rational function has a horizontal asymptote, right? Because that's exactly the definition of a horizontal asymptote. So this is actually stuff we already know about. We learned in college algebra or even before in algebra 2 in high school, right? We know about horizontal asymptotes. So for this limit of this rational function as x approaches infinity to exist, that means that this rational function has to have a horizontal asymptote. And if it doesn't, then the limit doesn't exist, okay? So let's look at this rational function and see if it has a horizontal asymptote. So I know a shortcut, and maybe you do, but if you don't, the shortcut I know is that if the highest power in the numerator and denominator are the same, which they are in this case, we have x to the first and x to the first, right? So the highest powers in the numerator and denominator are the same, then that means the horizontal asymptote is just my leading coefficients, the ratio of my leading coefficients, right? So in this case, the limit of this rational function as x approaches infinity is just the same thing as the horizontal asymptote, which is just 2 over 5, all right? So what about this next example, the limit of this rational function as x approaches infinity? Well, does this have a horizontal asymptote? So I remember 3 rules. When the leading powers are the same in the numerator and denominator, when the numerator is less than the denominator, and the numerator is greater than the denominator. So I showed a case of each of these 3 rules, okay? Each of these 3 sort of shortcuts, not rules, they're kind of shortcuts, okay? So when the highest power in the numerator is less than the denominator, what's happening as my x values are getting bigger and bigger and bigger? Well, that means my y values are approaching 0. And the reason why is because this x squared is increasing a lot faster than this x is, right? So what happens as a denominator gets bigger faster than a numerator, as the denominator gets bigger, the value of the entire ratio gets smaller, right? It heads towards 0. It doesn't necessarily get smaller, it heads towards 0, okay? So in this case, the horizontal asymptote for this rational function, okay, is 0, which means the limit as x approaches infinity is 0. So what about this last example? We have the numerator, the highest power in the numerator is bigger than the denominator, which means there's no horizontal asymptote, okay? So if we want to be specific, we can say that we have an infinite limit. We can say that this goes toward infinity, all right? But technically the real value limit does not exist. It just keeps going up like this. Okay, so this does relate to horizontal asymptotes that we learned in algebra, and also directly relates to end behavior if we learned that in algebra as well. So here are 3 examples and just some quick shortcuts. The examples can get more complicated where sometimes if you're unsure, you do have to divide the numerator and denominator by the highest power in the denominator. That is one trick you can do, and maybe that's how your instructor taught you. But for most examples I've found, you can just use these shortcuts and use this way of finding the horizontal asymptote, and that will be the limit at infinity. So hopefully this makes sense. All right, hopefully this video helped. If it did, make sure to hit like below, leave a comment as well. And if you want to see more content, I got more videos coming, so make sure to subscribe for more. But most importantly, keep flexing those brain muscles. I'll see you on the next video.